Something was detected beneath the ice of Antarctica, and it was never meant to be confirmed. In 2012, satellite scans from multiple agencies began picking up a massive geometric structure buried deep under the ice shelf. At first, it was dismissed as a sensor error. The readings didn't disappear. They repeated. Different systems, different countries, same location. Radar began showing straight edges, repeating angles, and hollow spaces far beneath miles of ice. One report called it inconsistent with any known geological process. Researchers tried to verify the data, but access began quietly tightening. Files were restricted, personnel reassigned, and the anomaly stopped appearing in public datasets. Internally, it was no longer called a formation. It was labeled Sub-Ice Anomaly Site. Then came the signal, a low-frequency burst recorded beneath the ice shelf. 3 pulses, a pause, then 3 more. Structured, intentional, impossible through that density of ice. The recording lasted seconds before everything returned to normal. No official explanation was released. The data vanished from public archives, but internal notes still referenced it as unlikely natural interference, and in newer scans the same geometry still appears, then disappears when examined too closely. Because the real question was never answered. If something exists beneath miles of untouched Antarctic ice, how long has it been there? And why do detailed scans always seem to stop right before the truth becomes visible? Because the real question was never answered. If something exists beneath miles of untouched Antarctic ice, how long has it been there? And why do detailed scans always seem to stop right before the truth becomes visible? In later reviews of archived datasets, analysts noticed something even more unsettling. The cutoff points in the data weren't random. They aligned too closely with the moment resolution became high enough to distinguish clear structural definition. It was as if clarity itself triggered loss. Some researchers proposed that this was simply a limitation of imaging through extreme density and interference layers. But that explanation failed to account for why multiple independent systems, using different methods, all produced the same abrupt drop at nearly identical thresholds. A small group within the research community began referring to it informally as a visibility boundary, not a physical barrier, but a consistent point where detail collapsed into noise. The deeper the scan attempted to go, the less stable the returned image became. What made this more disturbing was the repetition across time. Older scans, newer scans, even enhanced reconstructions, all followed the same pattern. The structure remained present, but never fully resolved. Always partially visible, never fully understood. And then came the final complication. In the most recent reprocessed datasets, faint secondary patterns began appearing near the main structure. Smaller geometric formations, previously unnoticed, arranged in ways that suggested the main anomaly was not isolated, but part of something larger. Something that still sits beneath the ice and still refuses to be seen completely. Around that time, a quiet shift began in how the data was handled. Instead of open collaborative review, analysis became compartmentalized. Teams no longer saw full data sets. Each group received only fragments, limiting any complete reconstruction of the anomaly across systems. Even with restricted access, patterns still emerged. Independent groups comparing notes unofficially noticed the same issue. Every partial dataset pointed to the same geometry beneath the ice, but none could produce a stable, full image when combined together. A few researchers suggested this was intentional limitation, not technical error. The idea was not that the data was missing, but that it was being prevented from forming a unified picture. That theory was never officially supported, but it continued circulating privately. At the same time, satellite monitoring above Antarctica showed brief anomalies and signal reflection patterns. These weren't strong enough to be classified as events, but they repeatedly aligned with moments when subsurface scans became partially clearer. The correlation was too consistent to ignore. Whenever subsurface definition improved, atmospheric readings above the same coordinates shifted slightly. It suggested a link between what lay beneath the ice and what was happening above it in real time. This led to a more cautious approach in later reviews. Instead of full scans, systems began using staggered imaging passes. The goal was to avoid triggering whatever was causing interference, while still attempting to gather usable structural data. But even staggered scans produced the same limitation. The moment resolution crossed a certain threshold, data degradation occurred. It was as if the system itself reacted specifically to clarity, not to observation in general. A few engineers began testing alternative imaging angles, hoping to bypass the degradation threshold. Different orbital positions, different sensor frequencies, different processing filters. But every variation led to the same result once the structure became too defined. The anomaly did not behave like a typical subsurface formation. It did not become clearer with better tools. Instead, it appeared to resist clarity itself, collapsing only when resolution reached a level capable of distinguishing full structural geometry. That led to a growing internal concern. If the structure was natural, no such consistent response should exist. But if it was artificial, the behavior suggested something far more unusual. A system reacting specifically to observation thresholds. During one extended review cycle, a technician noticed something subtle in older datasets. The earliest scans, decades prior, contained slightly more coherent outlines than modern reconstructions, even though imaging technology was far less advanced at the time. This contradiction became difficult to explain. In most scientific fields, improved technology leads to improved clarity. Here, the opposite appeared to be true. The more advanced the system, the more unstable the final image became. Researchers began documenting what they called resolution collapse points. These were specific thresholds where increasing clarity did not reveal more detail, but instead introduced structured noise that obscured the same region repeatedly. Across multiple datasets, the collapse points aligned almost perfectly. Regardless of sensor type or agency, the same depth beneath the ice produced identical breakdown behavior. It suggested a fixed boundary in how the region could be observed. As more data accumulated, analysts began re-examining older anomalies that had been previously dismissed. Some faint signals, once labeled as noise, now appeared structured when viewed alongside the newer collapse patterns from the Antarctic region. This raised a troubling possibility. The anomaly might not be isolated. Instead, it could be part of a wider pattern of observational interference occurring across multiple datasets, only becoming visible when compared retrospectively. To test this, a limited cross-reference was attempted between different satellite archives. The results were inconsistent. Some systems showed alignment and distortion timing, while others showed complete data divergence, as if filtered through different realities. Despite inconsistencies, one detail remained constant. The Antarctic coordinates always produced the strongest and most repeatable collapse behavior. No other region on Earth demonstrated the same precision in response to high-resolution scanning. A small subgroup within the analysis teams began proposing a more cautious interpretation. Instead of asking what the structure was, they began asking what conditions were required for it to remain partially visible at all. That shift in perspective changed the entire approach. Instead of trying to fully resolve the image, researchers began studying the boundary itself. The exact point where clarity transitioned into distortion became the primary focus of investigation. What they discovered was unexpected. The boundary was not static. It shifted slightly depending on observation intensity, suggesting that the limit of visibility was not fixed, but responsive to the act of measurement itself. This discovery changed the tone of the entire investigation. If the visibility boundary shifted based on observation intensity, then the act of scanning was not passive. It suggested the system was responding in real time to how closely it was being examined. Engineers attempted to confirm this by repeating identical scans under controlled conditions. Each pass used the same equipment, same orbit, same processing pipeline. Yet the collapse point still shifted slightly with each successive attempt. That inconsistency became difficult to dismiss. If hardware and conditions were identical, then the only variable left was the system being observed itself. Something about repeated attention seemed to destabilize the clarity of the result. During one internal review, a senior analyst noted a troubling pattern. The longer a scan focused on the same coordinate set, the faster the data degraded. It was not random corruption, it followed a measurable acceleration curve. This meant prolonged observation produced diminishing clarity. Instead of revealing more detail, sustained focus reduced the amount of usable information. The region became harder to interpret the longer it was watched. At this stage, some researchers began avoiding continuous monitoring altogether. They switched to brief, intermittent scans in an attempt to preserve data integrity. Even then, the collapse threshold remained consistent across all attempts. But intermittent scanning introduced a new problem. Each new dataset appeared slightly less stable than the previous one, even when conditions were unchanged. It suggested the system retained a form of memory between observation cycles. That idea system memory was initially dismissed as misinterpretation. But, as more datasets were compared, a consistent degradation trend appeared. Each return scan produced slightly more noise than the last, even when no changes were made to equipment or orbit conditions. Then came the most significant event in the entire investigation. A scheduled, high-resolution pass aligned perfectly with optimal atmospheric conditions. For the first time, engineers attempted a full-depth reconstruction using combined multi-system data. For a brief moment, the structure beneath the ice became fully visible, not fragmented, not distorted, complete. Defined geometric layers extended deep into the subsurface, forming patterns too precise to be explained by natural ice or rock formations. That clarity lasted less than 10 seconds. At the exact moment full resolution was achieved, every monitoring system involved in the scan experienced simultaneous signal collapse. Data streams did not just degrade, they terminated abruptly. When systems recovered, the complete image was gone, not partially corrupt and missing entirely. In its place, only low-resolution noise remained, as if the moment of clarity had never occurred within the recorded datasets. Internal logs confirmed something even more unusual. The failure did not originate from a single system. It occurred simultaneously across all participating sensors, regardless of manufacturer, orbit, or processing architecture. A post-event review classified the incident as multi-system synchronization failure under extreme environmental interference. But the wording did not explain why only one specific coordinate produced identical collapse behavior across all platforms. After the event, access to the full-resolution dataset was immediately restricted. Not deleted, but segmented across separate archives. No single team retained the complete version, making reconstruction of what was seen in those final seconds effectively impossible. Attempts to rerun the same scan conditions failed to reproduce the result. Every replication produced earlier stage collapse, never again reaching full structural clarity. It was as if the system no longer allowed that level of visibility to occur. In the following weeks, researchers noticed something subtle but consistent. The region behaved more conservatively under observation. Collapse occurred earlier in the imaging process than it had before the full resolution event. That shift suggested a lasting change. Whatever had been briefly observed was no longer accessible at the same threshold. It appeared as if the system had adapted, lowering the point at which clarity would begin to fail. Internal discussions grew more restrained. The focus shifted away from attempting full reconstruction and toward understanding why the threshold itself had changed after a single moment of complete visibility. One final memo circulated quietly among senior analysts. It stated that no further meaningful resolution of the target structure is currently achievable under existing observation parameters. That statement effectively ended active investigation into the anomaly. Officially, research continued in reduced form. Unofficially, the region was considered observationally unstable beyond a certain depth of analysis. And yet the data never fully disappeared. It still exists in fragments across multiple systems, waiting for the moment someone aligns them correctly again. Because the real question was never answered. Not what is beneath the ice, but why it only becomes visible when everything else starts to fail. Something is still there, and it has already shown it can respond the moment we try to see it clearly.